common emitter amplifier in figure 1 has been calculated in question 4 of tutorial 5 to be IC equal to 50 microamp and VEC to be 10.86 volts. The PNP transistor Q1 has all this. Assume that the capacitor have infinite values. What are the voltage gain, input resistance, output resistance, current gain, if all these are given? So we need to find 1, 2, 3, 4 of this. We'll start with the input resistance, followed by the voltage gain, then output resistance and current gain. Usually we'll start with input resistance, then followed by voltage gain, for the reason that we'll see later. Now, as the DC parameters value already be given to you, there's no need to do DC analysis again. And we will now proceed with the AC analysis. For AC analysis, let's look at this figure. As given in the question, the capacitors have infinite values. The impedance of the capacitors is just 1 over omega C, taking in modulus. So if C is infinite, then 1 over omega C is equal to 0. So it's basically short for AC. So all these capacitors C1, C2, C3 are all shorted for AC analysis. For AC analysis, another important thing is that the DC sources, which is this and this, are both grounded, connected to ground, 0 volt. With that, you'll be able to get the following figure. Here. For emitter, it's connected to RE1 to ground. Emitter is connected to RE1 to ground because C2 is grounded. For collector, is connected to RC to ground, connected to RL to ground. And for the base, is connected to R2 to ground, R1 to ground, connected to R1, this is shorted, to RI, VI to ground. Base connected to R1 parallel R2 to ground, connected to RI, connected to VI to ground. And this is the AC equivalent circuit. To get small signal AC equivalent circuit, replace the transistor with the small signal model. This is the small signal model. This is a PNP, whether it's PNP or NPN, you have the same small signal model. Between the base and emitter, you have R pi. Between the collector and emitter, you have these two components. One is a current source, GMVBE. Even for this PNP, the current also flows from collector to emitter. Okay, you also have a resistor called R0. Now, listen carefully. For voltage gain, input resistance, current gain, you can ignore R0 in the calculation unless told otherwise. What do you mean by ignore? As R0 is very large, when you analyze the voltage gain, current gain, input resistance, the effect of R0 is very, very little, very, very small. You can take R0 to be open because it's very large resistance. However, for output resistance calculation, you cannot ignore R0. If you ignore R0, you will not be able to find the Rout, the output resistance value, properly. Let's continue with the small signal AC equivalent circuit drawing. Let's start with emitter. Emitter is connected to RE1 to ground. Collector is connected to RC, connected to RL to ground. Base is connected to RB to ground. connected to Ri, Vi to ground. With that, we have the small signal AC equivalent circuit. One thing to note is that with R0 open, IC is basically equal to GMVBE, and GMVBE is equal to beta IB, which is equal to IC. GM is equal to IC divided by VT. As we know IC from tutorial 5 question 4, you can find GM. R pi can be obtained once you obtain GM, and R pi is 50 kilo ohm. R0 is equal to this. For PNP, we just put modulus across the VCE, and you have this, and the V and the R0 is equal to 1.72 mega ohm. Now we will try to find the input resistance. For input resistance, it's just the resistance looking into the input of the transistor, excluding the source resistance. Source resistance is the resistance that is connected to the source. This is the source. When I look inside, I see input resistance. If I know the resistance looking into this point, and I name the resistance to be RK, so RK parallel with RV will give me Rin. And how do we find Rin? We will first find RK, then RK parallel with RB to find Rin. So we can draw this in a simple form, where the voltage here is VB to ground, the current going into VB is IB, and this point is connected to RE to ground. For input resistance, you can ignore R0, we can open R0, so the current GMVBE, which is equal to beta IB, flows down. With that, we get this. Note that what we are trying to find is RK, which is the resistance looking into this point, and is equal to VB divided by IB. How do you find a resistance? It's just having a voltage, identify the voltage, identify the current. Voltage VB divided by IB will give you the resistance, in this case RK. And in order to solve for VB divided by IB, simply write a KVL equation down. VB is equal to the voltage drop across R pi. R pi times IB is the voltage across R pi plus the voltage at this point. As the current IB flows down, beta IB also flows down. The total current flowing across RE is beta IB plus IB. Multiply with RE will give me the voltage drop across this point to ground, plus the voltage drop across R pi give me VB. Take all the IB to one side and put it down, you get VB divided by IB equal to RK, and RK is equal to R pi plus beta plus 1 Re. So Rin is equal to Rb parallel with Rk, where Rk is equal to this. Rin can then be calculated to be this. Next, we will